So with where we were from yesterday, we started with means as opposed to proportions. We haven't gotten all the way through this yet, but talking through it, we're going to get to writing this down today. State. What's going to be in state? What was in state? Population and sample. We're probably still going to do that. Then with proportion, we defined what? P. Now we're going to define what's closer to P. P is proportion of the what? Population. So we're not going to define X bar. We're going to define which one of the population? Mu. But that one problem defines it with X bar, and I don't love that. Plan. We check two things. What's the first thing we check? 10% condition. That's the same. We keep it. The second thing we need to do is check for what? Normal. We've only talked about one piece yesterday with normal, and we said we can use a normal approximation if what? If the problem says that the what is normal. Which distribution? Population distribution. So if the population distribution is normal, we can use a normal approximation. So theoretically speaking here, let's unfreeze the board. If this were a distribution of grades, now this one doesn't tell us normal. We're going to get to that. We're not at that point yet. Does that look fairly normal? It looks fairly normal. That's probably not a big deal. Like that's probably one we could use. It definitely peaks at 83 to 90. There are some grades that go, did I freeze it? Unfreeze it yet? There are some grades that go above 104. There's a section of like 8, 7, 8, something like that, that go between 97 and 104. So this distribution right here looks fairly normal, approximately maybe. And are those good grades or bad grades? Is that a good class set of grades or a bad set of grades? That's pretty average, pretty about what you would expect. Well, maybe a little higher, that we would expect that many between 83 and 90. What if I told you that wasn't the whole distribution? And there's the rest of it. So remember how I told you chapter 7 is going to split the people that know and the people who don't? What happened a little early? These are actually your test grades. So we've got this section over here of the people who are, okay, yeah, I'm good. And this section over here that's when I said I was going to do seating and say, if you don't care, sit in the back. There's my section. This is before I ever said the test grades distinguish the difference between those who are trying and those who are not. Keep that in mind as we finish this chapter. Put yourself on this section, not on this section. Okay, so now relating that back to where we are right now, could I take samples from this population distribution and say they're approximately normal? No. So that's where we actually are today. Yes, I wanted to tie that in, but now we got to see what happens if we take it from a distribution that is not approximately normal. So I got to pull up that link that I had yesterday. All right, so yesterday when we did this, I had a population distribution that already started out as approximately normal. I can actually change this to be whatever I want it to be. Let's say I want it to be extreme, and I want it to be like really right skewed. So if I take samples of 5 and calculate the mean, so I just took 5 samples. I talked about I can do animated like that. If I take samples of 5, what kind of distribution are we getting? Is that perfectly normal? It's not perfectly normal. some people might say approximately normal, approximately bell-shaped. What does it do a little bit still?
Right.
It's still got a little bit of that right skew to it. So I'm going to compare still with the same distribution, maybe even a little bit more extreme. And I'm going to do one with the sample size of 5 and one with the sample size of 25. And I'm taking the mean of both of them. So as my sample size gets bigger, what happens to my standard deviation? It gets smaller, so we're definitely seeing that part already. So I'm going to start doing a whole bunch of them. What can you tell about the shape of this one versus this one? The shape's a little bit more spread out. Yes, obviously, which is definite because we were talking about with the spread thing. What else? What is the shape of this one versus this one? I'm starting a whole bunch of them. And now it's kind of hard to see from where you are. I'm going to fit a bell-shaped curve to it. And I don't know how well y'all can see that from where you're sitting. But see how this one fits it a little bit better than this one? This one is still slightly right skewed. So as we change our sample size, we already know that our variation decreases. So also as the sample size gets bigger, what happens to the shape? It becomes more what? Becomes more bell-shaped. It gets closer and closer to normal. Trying to do one that I exaggerate even more. So like that one, you can see, we still see a little bit of that right skew here, but we see it a whole lot less when we get to 25. So going to the notes that are in front of you on the part that we have not filled in yet. So most population distributions are not actually normal. Now, there actually are a whole lot of things in real world that are fairly normal that we deal with on a regular basis. Height, IQ, your SAT scores actually are made to where they have to fit a normal curve. Like that's the whole point of making them a normal SAT score, is they switch them to be a normal curve. A lot of things that occur naturally actually do fit a normal distribution, but not everything. So what is the shape of the sampling distribution of X bar when the population isn't normal? What we just came up with is the sample size increases, the distribution of X bar changes shape. So as our sample size increases, it looks less like the what? So with this one looked more like what? What's this one called? What is this actual distribution called? The population distribution. So it looked less, as the sample size increases, it looks less like the one it came from, which is the population distribution, and more like what? It looks more what? Yeah, just said this. More bell-shaped, more symmetrical, more normal. So y'all can fill in those blanks while I'm getting this set up. So it's less like the population distribution, more like a normal distribution. Now, the only thing I don't like about this simulation thing website is that your sample size stops at 25 is the highest it lets us go. But we don't actually see central limit theorem until we get higher than that. So when the sample size is large enough, the distribution of X bar actually becomes very close to normal. This one's population distribution. Now, this is what we deal with as far as this class. We say if the sample size is at least 30, that's enough to be able to say we can use a normal approximation. So if our sample size, oh, got two blanks. Sample size will be, if the population is not normal, the sampling distribution will be, what do we always say here? Not normal, but not exactly normal, but approximately normal. If our sample size is at least 30. Now, I can't give you a good answer for the reason why it's 30, because when you get into farther statistical classes, that's actually not a real number that you should use. But for the level of what we deal with, we consider that the cutoff to be what we consider enough. So there's not like a statistical reason for the number of 30 because it's really not a number. But we deal with it as far as 30 is enough, what we call, to make it to where we can say it's approximately normal. So even if the distribution is not normal, so if we use a distribution that looks like this, as long as we are taking sample sizes of at least 30, our distribution of the sample means would still end up approximately normal. But we actually couldn't use a sampling distribution because there are 72 students in there. Why couldn't we use the whole sampling distribution then? What would our other issue be? We need to take at least samples of 30 to be able to get the normal condition to work. But what other issue would that bring up? My population size isn't at least 10 times my sample size, so we wouldn't be able to go through the whole process with this one. All right, so normal condition for sample means if the population is normal, so if it is stated that the population distribution is normal, then the sampling distribution of X bar, what? Y'all should know this answer. Like, we're just rewriting it. If I tell you the population is normal, you tell me the sampling distribution of X bar is what? Approximately normal. That was yesterday. This is true no matter what the sample size is. If I'm taking it from a distribution that's already normal, my samples should have sample means that are approximately normal. If the population is not normal, then what we're dealing with is called the central limit theorem. Very vaguely, that central limit theorem is like how I talked with dots yesterday. How I talked with these dots, and the average would be here and here. It's kind of like those dots are more towards the center for the means than the dots are for the individuals, is kind of where that's coming from. So if population distribution is not normal, the central limit theorem tells us that the sampling distribution of X bar will be what? Not exactly, but if what? So this is basically our checking normal condition for means as opposed to proportions. I'm going to split this into a couple videos today. Go ahead and I want to go over homework.